Some people are on and off. They're logging in again, leaving the meeting. Okay. So now we'll move on to our today's session. Video. Now we'll move to share the screen. So are you able to see the slide? First slide. Hello?
Yes, sir.
Yeah. Okay. Oh, so welcome to the second lecture. So in this lecture, we are in the unit 1. So we are going to see about the axioms in more detail. Okay, so in the last lecture, we just introduced the axioms of probability. Right. So probability it's a mathematical framework to reason about uncertainty, and it helps in developing approaches to inference problems. Okay. So we'll see what are inference problems. Okay. So to reason about uncertainty, we introduced some new concepts in the last lecture, right? So we introduced the concept of a random experiment, and then we described what is known as a trial. Okay? So a single performance of the experiment is called a trial. All right. So and then for each trial there is an outcome. Okay. So these are all basic ideas through which we established a mathematical model called as probability. Okay. Right. So now we'll see all, and then okay, once we declared what is an outcome, so based on the outcomes we saw what is a sample space, and then we saw what is an event. Okay, all these things we saw just as vague concepts. Okay, so we saw them in some introductory as some introductory concepts. So now in this lecture we'll see some more details of what is a sample space, what are events, and how we are assigning probabilities to events. Okay, so how what are the axioms of probability that those events should satisfy? Okay, so what are the basic ground rules those probabilities that we assign to those events should satisfy, so that we can use the theory for practical purposes. Okay, so the axioms are made in such a way that the results we obtain through this probability theory, or the results we obtain through these rules, are meaningful in a practical sense. Okay, so we'll go through. We also see some simple examples of calculating probabilities and applying those axioms. Okay, so this is the outline of today's session. Okay, so moving on to the session. Okay, now sample space. Okay, so what is a sample space? Okay, so considering our random experiment example, a sample space is the list of all outcomes. Okay, so when we do a random experiment, so we can consider some examples. Okay, so consider the example of flipping a coin. Okay, so flipping a coin can be a random experiment. Okay, and then we can also consider rolling a die, a single die. Okay, or picking some cards in a game, a card game. So these are all elementary examples. So through which we can understand what is probability. Okay. So now once we do an experiment, so as we discussed earlier, each performance of the experiment is a trial, and each trial results in an outcome, right? So now when we list out all the outcomes, okay, so for example, I conducted a random experiment and then I listed out all the outcomes. Okay. So say I'm listing it as A, B, C, D, etc. Okay. So I'm not going to a specific experiment, I'm just giving in a general sense. Okay. So A, B, C, D are outcomes of the experiment. Okay. So this is a list of all possible outcomes. Okay. So instead of saying as a list, I can say these are set of outcomes. I can collect everything together and then say that it is a set of outcomes. Okay. So sample space is the set of all possible outcomes. So for the coin tossing experiment, the set of possible outcomes will be heads or tails. Okay, so again we can collect all the outcomes together and then make it as a set. Okay. So we always refer to set theory when we describe the probability model. So always we describe everything in terms of set operations and the set definitions, etc. Okay. So now considering the sample space, so the sample space must satisfy some characteristics. Okay. So if we want to extract some meaningful practical results out of all our exercises in probability theory, the sample space we create should satisfy certain characteristics. Okay, so the sample space is the first step in modeling uncertainty. Okay, so when we are when we want to model something that is practically uncertain, so first step is creating the sample space, and then the sample space should satisfy certain characteristics. So what are those characteristics? The first thing is the sample space should be mutually exclusive. Okay, so the list of all outcomes, each outcome should be mutually exclusive. Okay, what does it mean? So for example, we have listed out A, B, C, D, different outcomes. Okay, so if A has happened, then B has not happened. Okay, so that is what is mutually exclusive. So if B has happened, nothing else has happened. A, C, or D have not happened. So similarly, C and D. Okay, so if one event has happened, it should ensure that the outcome we have listed should ensure that the other events have not happened. Okay, so that is what is known as mutually exclusive. Okay, so the outcomes in the sample space should be mutually exclusive. Okay, and then it also should satisfy collectively exhaustive. Okay, so what does it mean by collectively exhaustive? So once we conduct an experiment, we have not left out any detail of the experiment. Okay, so we have not forgotten to list out any even one of the possible outcomes. So that is what is known as collectively exhaustive. Okay. So the sample space should be mutually exclusive and it should be collectively exhaustive. So these are the two main requirements for a sample space to be practically useful. Okay, and then we also think about one extra property of the sample space, which is known as granularity. That is, by granularity, what we mean is the amount of detail that is present in the sample space. Okay, so amount of details we are capturing for the experiment. Okay, so take for example the coin tossing experiment. So we can just say that the coin tossing experiment is independent of any outside parameter. Okay, I just get head or tail. Okay, so I toss a coin, I just get head or tail. Okay, but we can perform if we are performing in this experiment, say outside on in an open space. Okay, so we can even capture some more detail which is surrounding the experiment. Okay, so say I can say one of the outcomes is head, and then I can say the other outcome is tail and it's raining outside, and then other outcome is it's tail and it's not raining. Okay, so you may argue that okay, whether it rains or not rains, how does it matter for getting head or tail, right? So, but if we have some belief that rain also affects the result of this experiment, we can include those details also. Okay, so the details what we are including, it is based on our understanding or our experience. Okay, so it is a kind of art. Okay, so it is we are to choose the right granularity. Okay, the right amount of detail in capturing a sample space. So this may seem frivolous, but it's also a legitimate sample space. Okay, so the second example where heads, we are capturing heads and we are also capturing the detail of tails and whether it is raining or not. It is also a legitimate sample space. But for practical purposes, we know we don't need such detail of other things. Okay, so a sample space is not always clearly defined. Okay, so it depends on how much amount of detail we want to capture. So that is what is the final summary of what we have discussed here. Okay. So if you have any doubt in this particular slide, you can just talk back. Have any doubt? Is that all? Are all the concepts clear in this particular slide? Yeah, one of you can unmute the mic and reply. Are the concepts clear, or are there something which is not understood clearly? Yeah, everyone. Hello. Any one of you just give me a reply. Unmute your mic.
Yes, sir.
Is the concept of granularity clear?
Yes, sir.
Okay. So we'll move on to the next slide. So we saw the concept of what is an event. Okay, so before that, we'll see some example of sample space. Okay, so here I have shown a discrete example. Okay, so sample space is a set. Okay, a set can be a discrete set or it can be a continuous set. Okay, so say for example, the set of real numbers between 1 and 20. Okay, so it is a continuous set. Okay, so there are infinite number of real numbers between 1 and 20. So it is an infinite set. Okay, and it is a continuous set. So if you just take the set of prime numbers between 1 and 20, so it is a discrete set. Okay, so here we are considering an example where the sample space is a discrete set. So what I have shown here is a tetrahedral die. Okay, so usually what we play is a cubical die. So here I'm showing a tetrahedral die. So we roll the die and whatever number comes at the top, so that is the outcome, right? So how many numbers will be there? So obviously it will be 4. The total number of outcomes will be 4 because the tetrahedron has 4 corners. So each corner is marked with a particular number. So in the front face you can see a 1, and on the top there is a 4 and 3, and the other corner is 2. Okay, so there are 4 different outcomes. So here I described a particular random experiment which is consisting of 2 rolls of a tetrahedral die. Okay, I'm just rolling the die once, and then I'm rolling it again, once again, and then I'm recording the first roll and the second roll. So what we get as outcomes? So all the outcomes, I'm listing it out as a tabular column. Okay, so as in a tabular form. Okay, so the x-axis represents say the first roll and the y-axis represents the second roll. Okay, so sample space. So in this slide we are seeing how to list the sample space. Okay, so how to list the sample space so that we can easily solve some practical problems. Okay, so one method of showing the sample space is using a diagram. Okay, so using a two-dimensional diagram, that is one method of showing the sample space. Another method is showing a tree diagram. So what you see on the right side is called a tree diagram. Okay, so both these diagrams are related. Okay, so the tree diagram is useful in some situations. The square, the two-dimensional square diagram is useful in some other situations. Okay, so once we have 2 rolls of a tetrahedral die, so obviously we will have 16 different outcomes. Okay, so are these outcomes mutually exclusive? Yeah, so they are mutually exclusive. So as we saw, they should satisfy two different characteristics which are mutually exclusive, and they should be collectively exhaustive. So once we complete the entire sample space, once we complete the picturization of the entire sample space, it should not leave out any outcome. Okay, so here we have 16 different outcomes which are shown by 16 different squares. Okay, so and we are even distinguishing between the outcomes 2 and 3. So the first roll results in 2 and the second roll results in 3. And then here we are capturing another outcome where the first roll results in 3 and the second roll results in 2. So similarly, we can write all the different outcomes in each of these squares. Okay, so this is a way of representing the sample space. So another way here, if you see the tree diagram on the right side. Okay, so here I have represented the first roll by a solid line. Okay, and the second roll is represented by a slightly thinner line. Okay, so the first roll can result in a 1, and then so it is a tree diagram where the leaves, so I can say, I can describe the thinner lines as leaves. So the leaves represent each and every outcome. Okay, so the first roll results in a 1, and then the second roll results in again a 1. So it is 1 1. Okay, so and then say first roll result in a 1, and then the second roll results in a 2. So all these are listed, so up to 1 4. So similarly 2 2 1 2 2 2 3 and 2 4. So we can list out all the outcomes at the end of the leaves. Okay, so similarly we have at the end 4 4. So first roll resulting in 4 and the second roll resulting in another 4. Okay, so each branch of the tree represents one outcome. Okay, so only the final end, the end of the leaf is known as the outcome. So whatever we see at the end of the thicker line, so these are intermediate results. Okay, so these should not be uh, named as outcomes. So you can see 1 2 3 and 4 at the end of the thicker lines. So these are not the actual outcomes. So only the final end result is called the outcome. Okay, so these are all terminologies which we clarify in the first place itself, so that we won't have any ambiguity later on. Okay, so this is the description of a sample space, which is a discrete sample space. Okay, so we can also define some continuous sample spaces. Okay, so yeah. Okay, so now we consider events. Okay, so let's come to events. So we consider a subset of the sample space and then assign probability. So while constructing a probabilistic model of some uncertain event in real life, so we consider a subset of the sample space and then assign probabilities to those subsets. Okay. So the subsets are given a special name, which is event. Okay, so an event is a subset of sample space. So in general, we assign probabilities to events as opposed to individual outcomes. Okay, so instead of giving probabilities to, so when we are constructing a probabilistic model, so first step is to assign a sample space, or sorry, first step is to list out the sample space, and then to each element of the sample space, we have to assign some probabilities. Okay, so it is not always good to assign probabilities to individual outcomes. So that is why we come to the concept of events. So why do we not assign probability to individual outcomes? So we'll see what is the difficulty in considering only the individual outcomes. So consider this example of a dartboard, a circular dartboard. Okay. So I assume you are familiar with what is a dartboard. So it is just a small game where we just throw arrows, and the arrows land on a particular point in a, say, a cardboard kind of surface. Okay. So a dartboard can be considered as a, so this throwing an arrow on the dartboard can be considered as a random experiment. Okay, so the point where the arrow lands is a random point. Okay, so someone throws an arrow, so inside the circle the arrow can land at any random point. Okay, so this is a random experiment. Okay. So now the sample space of this experiment can be the set of all points inside the dartboard. Okay, so the dartboard can be considered as a circle. Yeah, so it's actually a circle. So we can consider the circle situated at the origin. So we can have a coordinate system, and we can put the circle such that its center coincides with the origin of the coordinate system. Okay, and then we can describe the sample space as the set of all x comma y such that x square plus y square is less than 1. Okay, so I'm just for the case of for the purpose of simplicity, I'm just considering a unit circle. Okay, so I'm just assuming the dartboard as a unit circle, and then I'm saying the set of all points that are inside the unit circle constitute my sample space. Okay. So this particular case is a continuous sample space. Now assume I'm asking the question. So what is the probability that the arrow that I throw or the dart I throw exactly lands at the origin? So can you guess what is the probability that exactly at a single precise point I'm going to throw my dart or my arrow? So what is the probability of getting that? Anyone, can you please answer? Just unmute your mic and speak out. Is the question clear? Hello, students? Yeah, it is 0 because intuitively it is the
0.
point has very small area, right? So we cannot say that means we cannot assign any probability to a particular single point. Okay, so now if we consider all the points inside and say that probability of hitting here is 0, probability of hitting there is 0, so everywhere we say, so of course all the points are outcomes of this experiment. Okay, so but if we assign 0 probability to all the outcomes, we don't have any practical information, right? So we don't have any useful information about the experiment. So that is why we consider, instead of considering single points, we consider some areas. Okay, so just okay. So I'm not able to draw on this. Okay. So instead of considering single points, if we consider some particular areas inside the circle, okay. So if I draw some closed figures inside the circle, so those areas we can assign some probability. Okay, so for example, you can see the circle here. Okay, so what is the probability of throwing the dart on the first quadrant of the circle? So that has some finite probability, right? So always you can assign some probability for a particular area inside the circle. So say the first quadrant, what is the probability? Say the third quadrant, what is the probability? Okay, so what is the probability of throwing the arrow on the third quadrant? So that will be having some finite value. Okay, so okay, before even describing what is probability, I'm using the word probability. So instead of that, you can just consider what is the likelihood of throwing the arrow into the first quadrant. What is the likelihood of the arrow landing in the third, say the fourth quadrant or the second quadrant? So these likelihoods will have some non-zero value. So since these have non-zero value, we can obtain some practically useful results. Okay, so that is why we consider set of outcomes instead of set, or say a subset of outcomes instead of considering individual outcomes. Okay, so this slide explains what is the significance of events. Okay, so instead of considering single outcomes, we are always considering a subset of the sample space, which are subset of some outcomes. Okay. Yeah. So the main point to stress here is, so only if we consider some subsets of outcomes, we get some practically useful results. Okay. So and then okay, now again it is a revisit of our previous probability axioms. Okay. So in the previous slide, we said that we are assigning probabilities to individual events. Okay. So assigning these probabilities, there are different methods or different ways of assigning probabilities to individual events. Okay. So one method is to conduct the experiment for infinitely many number of times, and then see how many times those events occur. Okay. One other method is to see some patterns in the experiment, or to see some patterns in the way we conduct the experiments, and then to see some symmetries, and then arrive at some numbers. Okay, so these are the ways of assigning probability that we would have studied in the lower classes, right? So what we do is we say what is the total number of outcomes and what are the favorable number of outcomes. This is one method, and the second method is actually doing the experiment for infinitely many number of times. Say we cannot do it for infinite number of times, so we do it for large number of times, say 100 trial of a particular experiment, and in those 100 trials, how many times our favorable event has happened. Okay, so we are taking the ratio of the number of times that our favorable event has happened, and then at the divided by the total number of trials. Okay, so this is one of the method. So whatever method we follow to assign probabilities to events, whatever method we follow, this probability assignment should satisfy certain rules. So those rules are called what is called the probability axioms. Okay, is it clear? So what we are talking about? So we are assigning probabilities to events. Okay, so when constructing a probabilistic model, first step we have constructed what is known as the sample space. So we are coming to the second step. We are identifying some subsets of the sample space as events. Okay, so once we have identified some events, we are assigning probabilities to events. Okay, so we are just putting, okay, we are taking some event and we are saying that this is the likelihood that this event will happen. Okay, so it can be even our beliefs based on our experience. It can be our beliefs about the likelihood of events. Okay, so whatever we do, whether it is our belief about the likelihood of event, or we did some experiment and arrived at the likelihood of the event, or we saw some mathematical symmetry and then we arrived at the likelihood of those events. So anything, whatever, any method we use, that is called a probability law. Okay, so I think you can see the highlighted word in red. So whatever method we use to arrive at probabilities of events, it is called a probability law. Okay, okay. So now whatever probability law we use to arrive at the likelihood of those events, it should satisfy the three axioms. Okay, so the axiom one is the non-negativity axiom. So we want to work with positive numbers, and then the second axiom is a normalization axiom, where we restrict our probabilities to not exceed 1. Okay, so the probability of the certain event or the probability of the sample space itself is 1. And then the third axiom, so the third axiom, you can just see the picture here. So I just represented two sets which are disjoint, or we can say they are mutually exclusive, A and B. So the probability of union of A and B, which are mutually exclusive, is nothing but the sum of the probabilities of A and B. Okay, so this is the rule, that is, we choose the probabilities such that the probabilities of mutually exclusive events add up to give the probability of their union. Okay, so this is a simpler form of axiom 3, and then what I have mentioned here is a generalized form. So now we extend the concept of only two events to n number of events which are mutually exclusive. Okay, so that is the axiom 3. So axiom 3 is also known as additivity axiom. So I have also given the statement of the additivity axiom. So the probability of the event equal to the union of any number of mutually exclusive events is equal to the sum of the individual event probabilities. Okay, so here this slide is actually a revisit of our previous discussion in the last session, right? So we are just giving the axioms. So only thing is we are introducing a new concept called a probability law. Okay, so probability law is the method which we use to assign probabilities to individual events. Okay, so we are saying that the probability law should satisfy these axioms. Okay, so now we'll see some examples. Okay, now it's 10:35. Okay. So we'll see some examples of having a probability law, a particular type of probability law, and then how to arrive at some other probabilities in the random experiments using the probability axioms. Okay. Okay. Now consider this example. Okay, so this is again the same tetrahedral die example. So was what we saw in the first case. So I'm giving the same example. So now we assume a particular law which is known as a discrete uniform law. So I've highlighted it in red. Okay. So I'm assuming that all the outcomes are equally probable or equally likely. So I'm assuming a probability of 1 by 16 to each of these events. Okay. So this law is an assumption. Okay. So it need not be that it should be 1 by 16 for all the outcomes. Okay. So we assume that the die is a fair die. That is, its outcomes are actually random. Okay. So it is not a loaded die. So we have two different cases where we roll a fair die or we can roll a loaded die. The loaded die is it biases one particular outcome or some set of outcomes is biased in a loaded die. A fair die is where it is perfectly manufactured, so it doesn't give bias for a particular outcome. Okay, so if you assume the die is the tetrahedral die shown as a fair die, so we can very well assume that all the outcomes are equally likely. So this is actually representing our belief about the die. Okay, so I've given the probability of all the outcomes is 1 by 16. Okay, so now using this random experiment, so we have described the random experiment, we have described the events, so all the possible events, all the possible outcomes, and then we have assigned the probabilities. Okay, I have assigned 1 by 16 probability to all the outcomes. The outcomes are the squares here, so all the squares have probability of 1 by 16. Okay, now we can answer some questions. Okay, so what is the probability such that xy or the, so x and y represent, x represents the first role and y represents the second role. Okay, so what is the probability that the first role is 1 and the second role is 1, or the first role is 1 and the second role is a 2. Okay, so this case is represented by the blue shaded squares here, right? So what is the probability? Now we use our axiom 3, right? So we can see that this first square and the bottom left square and the one above it, are they are mutually exclusive, right? So now we can use our probability axiom 3. So by just using the axiom, we just add up the individual probabilities. So we add 1 by 16 plus 1 by 16, which gives us 2 by 16 as the probability of getting these two results. Okay, 1 1 or a 1 2. Okay, so you should be clear about what we are doing, right? So what we have done is we have first created a probability model for our random experiment. So the model consists of all the outcomes along with their probabilities. Okay, so all the outcomes are listed as squares or shown as squares, and for each square we have assumed a probability of 1 by 16. So all these steps constitute what is known as constructing the model. Okay, so once we have constructed the model, now we are using our axioms to arrive at some practical results. Okay, so you should note that when we assign the probability to each of the individual events, we are not using our axioms. Okay, we are using some other thing called a probability law. So once we have assigned it, after creating the model to arrive at some practical results or to answer some questions, we are using our probability axioms. Okay, so next I ask the question, what is the probability of always getting the first role as 1? So what is the probability? So can anyone answer?
4 by 16.
Yeah, can you repeat?
4 by 16, sir.
4 by 16, yeah. So it is 4 by 16 because the squares above the blue shaded ones also contribute to that particular set, right? So I can just, so the squares which are shaded green all constitute this particular event where the first role is a 1, right? So the total number of squares is 4, so it is 4 by 16. So that is the answer. So here what we are actually doing is we are using the third axiom, right? So we are adding up all the individual probabilities of the shaded squares. So 1 by 16 is added 4 times to get what is 4 by 16. Yeah. So and then can anyone answer the next question? Probability that x plus y is odd. That is the sum of the first roll and the second roll is odd.
1 by 2.
8 by 16.
8 by 16.
Yeah, 8 by 16. Good. So it's 1 by 2. So how we are arriving at that? Again, we are using the third axiom. So we are just selecting the squares which add up to the odd sum. Okay. So these are the squares which add up to the odd sums. And then, of course, we are seeing obviously it is the total number of squares is 8. So we add up 1 by 16 8 times, and then so it is 8 by 16. Okay. So answer the fourth question. Minimum of xy is 2. So what is the probability of the event? That
11 by
minimum
16.
5 by 16.
5 by 16. Very good. So I just shaded all the squares which contribute to that particular event. Okay, so total number of squares are 5. So I add 1 by 16 5 times, and then I get 5 by 16. Okay, so the process should be clear, right? So I assume that you understood the process of making a probabilistic model and then using that model along with our axioms to get the practical results. Okay, so now we will see another example. Yeah, so now this is a continuous sample space, right? So also it is also an infinite sample space. Okay, so here we are considering set of real numbers. So obviously the set of real numbers is infinite. Even if we choose two finite endpoints, the set of real numbers is infinite. So the sample space is represented here as a set, which says it is a set of all points x comma y such that x comma y is greater than 0 and less than 1. Okay, so all points on a square. So we can even consider this as a square dartboard. Okay, so we are having a dartboard which is in the square shape, and we are throwing a dart on it. So where does the dart land? Okay, so that is again, it is a random experiment. Okay. Now, as we saw earlier, individual points don't have any probability, right? So individual points on this very precise small points on this dartboard don't have any probability of occurring. Okay, so they have 0. So we consider areas instead of single points. Okay, so now to assign probabilities to those areas, okay, so or say we consider outcomes which are having finite areas. Okay, so we are avoiding saying we are avoiding asking the questions of what is the probability of my dart landing on a single precise point. Okay, so I'm just considering some zones. Okay, so I'm taking the square, I'm splitting it into some zones, and then for those zones I'm assigning some probabilities. Okay, so I'm constructing the model by assigning some probabilities to some identified zones. Okay, so now I can have any I can have what I can say is I can have different kinds of beliefs about landing my dart on particular zones. Okay, so for the case of simplicity, for the purpose of simplicity, I'm just saying that the probability of landing my dart on a particular zone is equal to the area of that zone. Okay, so I'm just simplifying it by saying that whatever area I'm considering, whatever say closed figure I'm considering inside the square, I say the probability of landing in that particular zone or inside that particular closed figure is equal to the area of that closed figure. Okay, so which is also known as a continuous uniform law. Okay, so whatever I have highlighted in red, it is just a particular type of belief system. Okay, so I believe my probability, my likelihood of landing the dart on a particular closed figure inside the square dartboard is equal to its area. So that is my belief. Okay, so now I have set up my probabilistic model for this particular random experiment. Okay, now I'm asking the question, what is the probability that x plus y is less than half? Okay, so what is the probability that I have landed my arrow on a particular point what is the probability that the sum of the x coordinate and the y coordinate of that particular point is less than half? So can anyone answer this question? So what is the probability that the coordinates of the point where my dot has landed add up to half or less? Okay, so here we have to consider a particular area, right? So what we can do is, so I'm just considering that as an equation and I'm drawing a line, right? So all the points that are below the line and fall within the square. Okay, so this triangular region, right? So this right angled triangular region near the origin, so that region represents my event, right? So that is the event that is mentioned in the first question, right? So what is the probability of getting that event? Considering that I'm assuming continuous uniform law, which says that means it is my belief that the probability is equal to the area of that zone what I have identified. So can you guess what is the probability there?
1/8.
1/8, correct. So it is the area of that triangular region. So half into half into half. So half into base into height. So it is 1/2 into 1/2 into 1/2. So that is the probability of landing my dot on that. So obviously it is 1/8. Very good. Okay. So now what is the probability of me landing my dot exactly on the point 0.5 and 0.3? So that is 1/8. Okay. Now I consider one point. Okay. So although I'm showing it as a small circle, so what I want is precisely at the center of the circle, I want to land my dot. So what is the probability? We discussed this earlier. So what is the probability of landing my dot exactly on the center of that red dot?
0.
Yes, yes.
0.
Yeah, louder. Yeah, 0. It's very good. So it's 0, right? Because of my assumption of the continuous uniform law, so any single point has 0 area. So obviously I have 0 probability of landing on a infinitely precise point on the square dartboard. Okay, very good. So these are the steps we follow in creating a probabilistic model and then obtaining some results. So in summary, what I want to tell is we are creating the probabilistic model by assigning some probabilities to events which are subsets of sample space, and then we are arriving at some practical results using our probability axioms. Okay, so these steps should be clear to you. Okay, okay. So with this I stop my session. So if you have any queries, yeah. So this is just considering a little more detail about what are the basic concepts that make our probability model, right? So, I'll stop sharing. Yeah. Yeah. So are the concepts clear for today's class? Okay, so are you able to follow the method which we are using? Okay, so first step is creating the probabilistic model. So there we are just assigning the probabilities. Okay, so there we are not using the probability theory. Okay, so assigning the probabilities based on our beliefs or based on our experience. Okay, whatever it is. Okay, that is a separate domain which is called the probability law. So once we have assigned the probability and created the model, after that whatever we do is based on the axioms or the probability theory. Okay, so is that concept clear? Or are you having any confusion in what we have discussed today? Is that clear? What are the steps we are going through and then using the probability theory? Okay, so I assume so anyone having any doubts here, please unmute your mic and speak up. Okay, so today evening you will have 3 quizzes. Okay, so many people didn't attempt the first quiz. Okay, so what I request is you whoever has already attempted the first quiz, I request them also to attempt it once again. So I will enable it. I will create it as a new quiz. Okay, so in the first session we had some confusions about how many students are attending the class, all those things. So I request you to attempt the quiz once again, first quiz. Okay, and also attempt the quiz for the second session and the third session. Okay, so today's session also. Okay, so quiz will be enabled by 6 p.m. today. Okay, okay. So this is what I want to tell regarding the quiz, and yeah, so attendance problem is resolved, and then okay. So I assume you don't all the concepts are clear considering today's session. Okay, and okay, so I think we can end the class now. Okay, so total 56. Okay, still many people have not attended the class. Okay, so class representative Manasa.
Yes, sir.
So please inform all the students who have not attended the class. Okay, so it's almost the third session now, and I am seeing it has never reached 59. Okay, so inform everyone. Ask them to attend the class.
Okay, sir.
Okay, so with this we come to the end of the class. Okay, so we'll see in the next session. So in the next session we'll see what is total probability, what is a joint probability, and we'll arrive at what is known as the Bayes theorem. Okay, so next session is a very important session which has a lot of practical uses. Okay, okay, so thank you for attending class. See you in the next session. Thank you. Wait, I'll take attendance.